Hello everyone, welcome to Computer Science E7. This is lecture 11, Color. So I know that you may wonder what on earth we could talk about with color, just like you may have wondered the same thing with the histogram, but rest assured that this is a particularly heinous topic, especially if you have looked at some of the color management settings in, say, Photoshop and been lost in these words that you know individually what they might mean, but put together they just become meaningless. And so that is part of what we are going to try to talk about today. So first of all, I did just want to mention a couple of things. So don't forget that the final project proposals were due today, but also we published the instructions for sending us your final projects. Realize that these are modified instructions for submitting files to us, because now we are allowing more than just images. So for example, if you were to create a book, for example, out of your images that you make for your final project, or a website or something like that, any type of file that is not a JPEG will be difficult or practically impossible to upload to Flickr. So we had to supplement that by rolling our own sort of submission code. So just to give you a very general overview, any images that you create for the final project and that are final images. So for example, if you make a book and you have, I don't know, a dozen or so images in that book or more, for example, then you will submit those JPEG files to us separately into Flickr, just as you always have with these assignments up until now. And so you'll give it a specific tag when you upload it to the Flickr group. I added it here, E7 final project, no spaces, and you can take a look at this page. So this URL is actually provided in the final project specification, but if you're curious, just offhand, it's cse7.org/final project. You'll be able to get all of these same instructions that I'm telling you now in print form, so that you can read it and go through it. So you will submit all of your images in JPEG form to Flickr, as you always have. Then if you have any supplemental files, so let's say you have a PDF of a book, or maybe you have a PowerPoint presentation, or a movie, or a collection of files that put together represent a web page, what you will do is send us those files via this upload form. And this form, you will basically log in, you'll authenticate with Flickr. That tells us who you are, and then you'll be able to upload all of those files to our server here, and then we'll be able to get the entirety of your final project and be able to get around Flickr's limitations at the same time. Keep in mind that there is also just a very short, basically how-to paper that we're hoping you'll write for the final project, or expecting you to write rather, for the final project. And that file, as it is also a supplemental file, should be uploaded here as well. So unlike previous assignments where we've had you email that to us, please don't email that to us. Just upload all of your stuff to the internet, the JPEG files to Flickr, and the paper and everything else to the website. And if you have any questions about that, we'll be able to clarify, certainly. And of course, I do want to mention that our first ever E7 field trip, I think, went over pretty well. So thank you very much, John, for organizing, and for all of you that came. It was a lot of fun, and the weather cooperated very well, I think, for some of the, or for the entirety of the day. Okay, so just as a quick reminder, as a quick review of some of the topics that we went over last week when we were talking about digital cameras specifically and the sensors within them, we broke down actually the components of the sensor, and we showed this particular diagram which represents, or which shows you some of the various items that can be found within a digital camera sensor. So the very top layer is a micro lens that focuses light that comes into the mirror box and focuses it down into the sensor well, because as you remember, there's a lot of electronics surrounding the very small portion that actually can detect the light. We want to be able to make sure that we can focus as much of that light as possible into that photodiode. Underneath the micro lens, we have a color filter array. This applies for most of the cameras, the digital cameras that are out there today, except for the ones that are of that Bayer type, if you remember, because that was a different type of sensor that removes the need for this color filter array. The point of this is that we can then recombine, using demosaicing, the colors that made up the particular scene at a later point in time. There is a missing layer from this excuse me, from this particular diagram, and that is the anti-alias filter that's usually found even it's on the very top, so even above the micro lenses. And the point of that is to get over these problems that we have with demosaicing, where because we have now a couple of pixels that have to be combined later on to represent one color, we can get these weird patterns that can emerge after we recombine this data, especially if the patterns are very, very fine on the sensor itself. And so the point of the anti-alias filter is to soften it a little bit, soften the frequencies or the high frequency patterns that are coming into the sensor, and soften it and be able to eliminate a lot of those problems. And so if we take a look then at the color filter array, we notice that most of them come in this particular pattern, what's called the Bayer color filter array. And there's a predominance of the green filters in this, and that is because, as we discussed, the green is the most important color for us to detect luminance, and the camera is able to use this to its advantage when it is recombining all of the data and creating not only the colors themselves in the final photograph, but also the luminance or the brightness of a particular pixel. And so as a result of this, because every pixel on this sensor can't detect all of the colors, we have, of course, that problem of needing to demosaic all of this information. So we have to later on recombine this data. So we take data from 4 neighboring pixels, recombine it, and then try to figure out what the original color was, what the original color might have been, and also what the original brightness might have been for that particular pixel. Now, also because of this problem, we also have fewer effective pixels. So the end result of the image, it has fewer pixels than the actual sensor has as well. And that is because these very edge-most pixels don't have neighboring pixels on this side to be able to compute any additional data for. And so it just becomes this problem. Well, you have to end it somewhere. You have to be able to end this demosaicing algorithm at some point, and that is why we have fewer effective megapixels. Now, one of the few types of sensors that don't actually require a color filter array, and remember there are different types of color filter arrays where they're in different arrangements, is this Foveon X3 type sensor. And we don't see very much of these, but they do exist. And the whole point of these is that we have at one pixel 3 different sensors that can detect each of the three major colors within one pixel. And so we can recombine this data later, but it's sharper, it's more accurate in terms of the detail, not necessarily the color itself, but in terms of the detail, because we don't have to worry about recombining this data with pixels that are neighboring of each other, that are neighbors to each other. And so we will be able to get much better defined details out of it. And so we typically find that the Foveon sensors have smaller, or rather fewer amounts of megapixels than a typical Bayer sensor. And that's from not only this reason that we have that much data to begin with, but also that the research just isn't there for these types of sensors. So these are, it's an interesting sensor, but it also has its downfalls as well. Like there's going to be more noise in the color regions because we have to recombine the data from these 3 sensors for that one pixel, try to figure out what the colors were originally for that. Keep in mind that so you'll notice that through this amount of silicon, the red light, for example, travels the farthest. And so if we have a photodiode at the very top layer trying to detect the blue wavelengths, we will get not only the blue, but also the greens and also the reds. So we get everything. We have to do something to try to figure that out. And try to figure out what just the blue component was later on. So we get this, we see this predominance in blue noise in these particular sensors because it is not very accurate. Then we talked about dynamic range and how, of course, if we're capturing an amount of light within a scene, we have this range from dark to bright that we can capture within the camera. And the sensor is responsible for the dynamic range that it can capture. So it has to do not only with the size of the pixels, but also how new the technology is and how little noise it has when reading these pixels. And after we capture this information, we have this problem of the sensor being this analog device. So it's not digital immediately. We have to convert it into a digital signal. And that is the job of this ADC, or this analog to digital converter. And what all that does is it just reads how full essentially that pixel is, and then it converts it to a binary number, and then it will be able to provide that binary number to the camera CPU to be able to process or to do something with. And we talked about how we can have a sensor that has very high dynamic range, but if we have an ADC that has a low sampling, then that could be bad for us, because we may not have then the tonal range within that within the possible dynamic range of the sensor, because we don't have enough values in the ADC to represent all of the values that the sensor can represent. So we typically see very high sampling bits from an analog to digital converter. Now, when we are capturing an image, so unlike our eyes, which play tricks on us when we're looking at objects that are reflecting or emitting light, these sensors, they are purely linear devices. So however much light they capture, that's how much light they will report. And so the results of this is, if you were to look at just the image as if it were linear and just completely off the sensor, it would look very, very dark, because it's not how we view the world. And so we have to apply what's called a tone curve to be able to map what the sensor actually reads to how we would actually view that particular scene. Somebody's very anxious out there to get their horn heard. Okay, anyway, this is a general type of tone curve that we see, and we even talked about a tone curve analog very early on when we did one of the software lectures. How if you remember that curves tool in Photoshop, what we were able to do was apply a tone curve of sorts to a file and make it a little bit contrastier or make it a little bit less contrasty. Realize that that's not the same thing, because normally you're already working on an image who has had a tone curve applied to it already. So you're not actually modifying the tone curve that made that image. You're just applying an extra one there. So in the camera or on your computer, when you're processing a raw file, you are applying a raw curve like this, or rather a tone curve, that overrepresents the middle few stops of the sensor. So basically it's placing the most importance on these middle few stops of the sensor, and less importance on not only the dark regions, the shadows regions, but also the highlights of that particular image as well. And so after this tone curve is applied, it essentially compresses the highlights and the shadows. And because in a JPEG, after it's been converted to a JPEG file or saved as a JPEG file, we have so few bits of data to work with, we are throwing away a lot of information at both ends of this spectrum. And so we use this as a reason, among many others, to use RAW over JPEG if you want the most quality out of your images. You will have the best ability to be able to modify them with the least impact on, or the least negative impact on quality. And as you'll see today, when we start talking about color, that same sort of thing applies even to a lot of these details that we'll be talking about today. So in order for us to really talk about color and how it works in the digital realm, we have to take another step back and talk about the eye again. So just as a quick review from many, many lectures ago, we talked about the eye and what the differences are between some of the cells that exist within the eye. So if you remember, we have, well, I mean, this is obviously an eye, and then we have the light that comes in. It's focused by the lens, it comes in through the iris, and it's focused basically everywhere on the back of the retina. But we have this portion of the eye called the macula, where we have the highest concentration of a particular type of cell. And this cell provides us with this detailed vision that we are very accustomed to having. And in fact, we have these two different types of cells within our retinas, the rod cells and the cone cells, and they do very, very different things. The rods, for example, they're responsible for night vision. And they detect motion very well. They're not really in the fovea, but they are scattered through, around it. So they are what predominates in your peripheral vision. And they're stimulated by monochromatic light. So they cannot view color, for example. This is opposed to the cones, which provides us our detailed viewing, the smallest 2% of our vision. So right in the center of our vision, we have a predominance of cones. It's less sensitive to light, which means that it's very good for day vision. It's concentrated in the fovea, as I said, right in the center of our vision. They are stimulated by color light, and this is what gives us our color vision. And they have a preference to detect detail. And so we showed this graph here, which, as you will remember, represents not only the rods and the cones, but we can further break down the cone cells into 3 different types of cells. So we have an S-type, an M-type, and an L-type, which basically signify what wavelengths of light we are able to detect with those particular types of cones. And as you might remember, we have, of these 3 types, the M and the L type are the most present in our fovea. So in the average person, it's about 98% of these 2 types of cells versus the poor little S-type only gets about 2%. And the dotted line here represents the response from our rod cones, or rather our rod cells. And as you can see, it drops off significantly right before the red. So because the rod cells don't actually get stimulated by red light, when you're, just as a quick reminder, when it's dark outside and you need some little bit of night vision, it's good to use very, very red light. So nothing that has a mix of light, but pure red light will not destroy your night vision because it's not going to stimulate your rod cells into readjusting for a brighter light. Okay, but anyway, you can see that we have a lot of things going on in our eye, and then all of these cells combine their signals, send them to our visual cortex in our brain, and we have to be able to figure out the colors that we are viewing, and this is done largely by the processing in our brain. And so we get a variety of wavelengths that are visible to us, all the way from 400 nanometers all the way up to just about 675 or so, which represents the spectrum of visible light that we can see. So color perception, this isn't the easiest thing in the world. It's difficult. It's not only difficult for us to understand how it works biologically, but it's also difficult for us to understand when we're viewing colors. And I say this because our brains play tricks on us. We don't see things the way they might actually exist in the real world. And I have a couple of fun examples to show you that prove this. So some optical illusions here. How many of you have seen this before? Oh, good, not many, so don't spoil it for the rest of us. But this is a particularly neat one. You'll notice that there is, say, a tile floor and there's some cylinder resting on it. There's a light on the far right, casting a shadow of that cylinder onto the tile floor. And you'll notice that 2 of the tiles in particular are labeled A and B. A way up here, B right here. Now, the neat thing about this optical illusion is that it's not really as it seems. So what is going on here is that the tile color A is exactly the same as the tile color B. And it's messing with our minds because we perceive this shadow here and we assume that it shouldn't be any lighter, or any darker, but it looks the same. I mean, it looks lighter, but it's actually the same. Okay, you don't believe me, so watch this. Okay, here, so I have this. All right, that's the slide, and what I'm going to do is bring up a color meter, which you might have seen me use before, and all it does is you can see that it provides a list of values in, and let's see, I'll do it in actual value. So you might recognize this as being red, green, and blue values, and a value of 0 through 255 for each. So this is a very quantifiable way of determining a color. So if I put it over this big block of red, you can see that it is predominantly red. Makes perfect sense. Do I have anything that's nice and green over here? You can see it's predominantly green. Okay, so let's do this for A. So you'll notice that I have my mouse right over the A tile, and it says that it is about kind of a middle gray, all 139s for these values. Now if I move down here, you'll notice that it says the exact same thing for B. Okay, there might still be some of you that are skeptical, because I know I didn't believe this at first either. So what I'm going to try to do next, if this will work for me, oh come on. What I'm going to try to do next, if this works, is try to bring this same image into Photoshop, and then we will try to do a modification to it that will hopefully make it a little bit more obvious. Oops. All right, so we have here, so it did something to the green color, but you can see that the optical illusion remains the same. And what I'm going to do is grab, let's see, place the file. I'm going to grab the eyedropper and record the color of that A slot. And so if I bring up the color meter, you'll see that it did pick that all 139 gray that we saw before. And then, then what I'm going to do is just paint like a little bit of a, let's see, I'll just draw a rectangle from A to B. And I will fill this rectangle with that gray, if this works. Oh, this is stupid. Smart, well, let's see. Try this again. That's stupider. Oh, this is, okay. All right, so here I have just filled it completely with that color. Now that there's this color bridge, you can actually see that they are the same color, but still it is playing a trick on our mind. And so the reason that this works is that you'll notice that there's these tiles here. So this is the dark tile in the section that does not have a shadow, and the shadow makes this dark tile get darker. And this, what was previously a light tile, now was, I mean, they just use the same color as the dark tile here, but because our eyes are used to, or our brains are used to seeing this pattern of dark and light and dark and light, it tricks us into looking at this in a very, very different way. Okay. Well, I always like that one. I think that's fun. But I have even yet another optical illusion to destroy your brain with. Okay? So as soon as my computer comes back up. Okay. Now I'm going to show you a picture. This is a picture that I took a long time ago. And I want you to stare at the black dot at the very center. And I promise nothing scary. You know, nothing is going to jump out of the screen. Nothing stupid or scary is going to happen. This is a legitimate optical illusion. And so I want you to stare at this. I'm going to talk about stuff for about 30 seconds while you stare at this. And what you will see when I change the slide, you may not actually notice that I had changed the slide, well, you probably will, but the slide will, it will be the same image, but the slide itself is going to have a slightly different color tint to it. And so it is this that I want you to pay attention to. And so somehow I managed to talk for 30 seconds without actually saying anything. So I'm going to switch to the next slide now. Okay, close your eyes, shake your head a little bit, and look at the slide again. Do you see what happened? So you saw for a brief second the inverse color. You saw the correct color for this image, which was a red building and a blue sky, when before you'd just been staring at the inverse, and then I flipped it over to this black and white, or this gray representation. And the reason that this works is that our eyes, or our cells, the cells in our eyes respond to various stimuli. So if there's a very strong predominance of a particular color, our eyes will try to battle that, and it'll get used to it. Very much like our bodies get used to pretty much any substance or any sort of stimulus we are able to ignore after a little while. The same sort of thing happens in our eyes. And so when we switch to this black and white one, we see the inverse of that color that had existed before. So I made this a few years ago, and I used to know how to do this, and I think it's pretty easy. I think all you have to do is you just take an image into Photoshop. You literally take the inverse of the colors, which is pretty easy. It's like, at least on the Mac, it's like an apple. I think it's the key Apple I, and then on a Windows machine, it's probably Control I or Alt I or something like that. And then you save that as a file. You put a black dot in the center. Then you just convert it to black and white and do the same thing. Put the black dot in the center. You'll be able to amaze your friends, just as I have done, hopefully, to most of you.